So welcome back. I'm Subhro Bhattacharjee. I'll be the chair of the session. So there has been a change in the schedule. Professor Zhaoqing Wang could not reach because of some visa issues, unfortunately. So Gang has kindly agreed to give one extra talk. So he would be talking about emergent quantum criticality from spin-orbital entanglement in G8 Mott insulators.
Yeah, thanks, Subhro. Yeah, so thanks everybody for being here in this late afternoon. So this is about emergent quantum criticality from spin-orbit entanglement in a D8 model insulator. Before I present the talk, let me just make a advertisement. So in 2020, 1.5 years from now, so there will be this 2020 highly fluctuating magnetism international conference on highly fluctuating magnetism. This conference will be held in Shanghai in 2020. So please be aware of this event and kindly register for this event. So this is the outline of the talk. So I first give some simple introduction to spin-1 quantum magnets. We know spin-1 is fundamentally different from spin-1/2. There's some interestingness about spin-1 quantum magnets, and then turn to spin-1 on diamond-lattice antiferromagnet, and give a couple of theoretical insights to understand some diamond-lattice-based antiferromagnets. There are 2 papers on this, and you can find some details about the content of this talk in these 2 papers. So the recent one is in collaboration with my student postdoc Fei Li in my group. So the Duncan Haldane was received the Nobel Prize for in 2006 for the study of spin-1 spin-1/2 chains. He pointed out that for spin-1 chains, if you have a Heisenberg interaction or something close to be Heisenberg interaction, so due to some non-trivial barrier phase effect, spin-1/2 chain is always gapless. Spin-1 is Heisenberg chain is gapped, and in addition to this gapped bulk in the chain, there is also so-called spin-1/2 edge states in the end. So later on, these 4 people, Affleck, AKLT, they together to construct AKLT state, which is the exact ground state for some specially designed Hamiltonian with spin-1 local moment on spin-1 on one dimension. So this exact wave function can be thought as follows. For each dot is a spin-1/2. They told 2 of them together from a spin-1 local moment, and this blue link means these 2 neighboring spin-1/2 from a total spin singlet. So if you cut these chains, in the end there will be an unpaired spin-1/2 local moment. That naturally explains there are edge states. These end states. So this as we know now, this spin-1 Haldane phase or spin-1 Haldane chain is an example of so-called symmetry protected topological order. So in this case, this protection is due to this Z2 time reversal or SO3's spin rotational symmetry. So after realizing that, Xiaogang Wen and his collaborator carried out a systematic classification of bosonic matters in various dimensions under the assumption of certain symmetries. They figured out a beautiful mathematical table to identify possible bosonic symmetry protected topological phases in every dimension. So they use beautiful mathematics to classify these. And it also turns out that the very well-known, very famous topological insulator in 2D and 3D is an example of forming SPT rather than bosonic SPT. So that guy is protected by time reversal symmetry. So these this forming SPT can realize in a non-interacting electron system. In contrast, for bosonic system like a spin degree of freedom or any kind of bosonic degree of freedom, they must have interaction to stabilize bosonic symmetry protected topological phases. Without the interaction, boson will always condense. So to fight against boson from condensation is to introduce interaction. So then the natural question is to going beyond this beautiful mathematical table is to understand the physical mechanism to realize the bosonic SPTs. So what's the physical system? Which physical system can potentially realize or stabilize? What kind of interaction can potentially stabilize bosonic SPT? That's one of the key questions in the field of this in this particular field. So following all these beautiful tables, so Senthil from MIT is a great Indian theoretical physicist. He wrote this very interesting paper, proposed this notion called topological paramagnet, and suggested the possibility or construct some example of topological paramagnet with a spin 1 degrees of freedom on a frustrated motor insulator, with frustrated spin interactions in a motor insulator in 3 dimensions. So topological paramagnet, as this notion invented by Senthil, refers to a spin SPT. It's a SPT with spin degrees of freedom. So they try to mimic the idea, mimic the example of Haldane chain in 1 dimension. So they propose the frustrated spin 1 quantum magnet are a natural setting to realize such SPT phases in 3D. So in the end of this very interesting paper, in the rather end part of the paper, they suggest or they propose or they speculate the possibility that a frustrated diamond-lattice, as SungBin has already introduced in the tutorial session. So if you have on a diamond-lattice, a forced neighbor interaction is not frustrated. If you introduce forced neighbor interaction, the diamond-lattice magnet can become frustrated. So frustrated diamond-lattice refer to the frustrating J1, J2 type of interactions. So the frustrated diamond-lattice with spin 1 is short range entangled. It's short range entangled. There's no long range entanglement here. Yeah. So the frustrated diamond-lattice model. So there is a bit speculated may support, such as this material manganese aluminite, copper aluminite, which belong to the general families of material of spinel of this kind of form, may potentially may possibly realize a topological paramagnet in a 3-dimensional system in 3D. So yeah, so this is the 3-dimensional analog of Haldane spin 1 phase in 3D, right? So following this suggestion, so experimentalist from Johns Hopkins University. Yeah, when the spin is classical. Yeah. No. In a larger spin, if a spin 3/2 or spin 1, spin 2, you can first treat the spin as a classical vector, then it's huge degeneracy.
Sure.
Then you turn on, you really seriously consider the quantum nature of the spin. Then you have a quantum 0-point energy. Then you lift the degeneracy, may have some particular order. But we don't know precisely how strong is the quantum effect. If you go to spin 1/2 J1, J2 model on diamond-lattice, which is not discussed here. We don't know the ground state, right? Yeah, maybe it's ordered. Maybe it's ordered. There is no numerical indication. J1, J2, spin 1/2, diamond-lattice.
It's Rotor with functional RG.
Yeah.
Which did the function of spin S and J2 over J1.
Yeah. So with FRG, they seem to suggest spin 1 may have some liquid phase somewhere. Yeah. So that paper come later after this experiment, our theory. Yeah. Yeah. Let me continue. So following this Senthil's suggestion, so these experimentalists they synthesize this material. They probably know this material before. So this material was discovered by Japanese group in the 1970s. So they synthesize this material. They try to attach this experiment or this material, the phenomena of this material to the topological paramagnet that was suggested by Senthil, right? So the recent theoretical, this is actually much mini abstract. where I first saw the result from multi-mixing abstract. So they suggest that the work like spin 1 on diamond-lattice would enable a novel topological paramagnet state generating fluctuating Haldane chains within the structure with topological protected end states. Yeah. So the limited information from the experiment is that this is the spin 1 magnet with the diamond structure and the nickel ion. And the system remained disordered down to 0.1 Kelvin. So there's no obvious magnetic order, freezing at all. In addition, there is a structure transition around the 400 Kelvin. So the symmetry is lower as you cool system at 400 Kelvin. So there is a cubic to tetragonal structure transition. Yeah, so that's the motivation, sort of the motivation and both theoretically and experimentally. Then we try to understand simply what does this material do. Forget about this theoretical motivation, just try to understand based on the existing experiment and structure information, what can one do to model this system. Yeah, so the first theoretical insight was just think carefully about the law of single anisotropy. For spin 1 local moment, actually is allowed, especially the symmetry is lowered at 400 Kelvin. So at below 400 Kelvin is below 400 Kelvin is the tetragonal symmetry. So the symmetry tells us, the lattice symmetry tells us there must be a single anisotropy. This is allowed by the lattice symmetry, but in the cubic phase it's not. There is no such single anisotropy. So the first theoretical insight by us is just to consider the role of single anisotropy. So we write down a minimum model. So this is so-called A-side spin nail, nickel rhodium oxide, nickel form a diamond lattice of this kind. And we consider J1 and J2 interaction. So as SungBin said, with only J1 interaction, the system is not very frustrated. You need to consider further neighbor interactions. So we consider a minimal J1, J2 model. In addition, supplemented with this single anisotropy. So this can be immediately checked. If one have single crystal samples, one can measure the Curie rise temperature. If one apply field in plane, out plane, along the z direction and normal to the z direction, they would have two different Curie rise temperatures. This can be immediately examined by experiment. So let's see what we have, what we know about this model. So if we don't have these single anisotropy, so this is just a simple J1, J2 model that has been studied by SungBin and Duran Bergerman and Simon Trebest, in more than 10 years ago. So this is just J1, J2 model. So first treating the spin as a classical vector, and the simple mean field theory tells us that the system, as you cool the temperature, the system do not know where to order because of there's a strong fluctuation. So the so-called spin spiral wave vectors, there are tons of these spin spiral, degenerate spin spiral wave vectors that give you the same, degenerate classical mean field energies. And these degenerate spin spirals, they form a surface, form a two-dimensional surface in a three-dimensional Brillouin zone. And this surface evolves as you change the parameter of J2 over J1. But as you cool the temperature, thermal fluctuation will lift the degeneracies, favor various magnetic order with certain spin spiral wave vectors. And for instance, for this one, we'll select these green points along 1-1 direction. And for this one, we'll select these momenta, these wave vectors near this 1-1 direction. And it continuously evolve as you increase this J2 over J1. So this is what we know classically about this model. Yeah. So what are we going to do? We're going to do something very similar, but something quite different. So we are this is the system remains disordered. So we better treat the spin in a quantum mechanical fashion. And this model has actual single ion anisotropic term. And in fact, we can imagine this term is very large. Imagine this single ion term is positive and very large. D is positive and very large. Then the ground state is extremely simple. It's a trivial product state. It's a trivial product state. and every side is SZ equal to 0 on every side. In this limit where this single anisotropy term is dominant. This is extremely simple, then we know the ground state. Now we want to, we do the following things. Imagine we decrease the single anisotropy and increase the super-exchange interaction, and we will see what happened to the system, right? We started from this well-defined limit, right? We know the ground state, and we increase the exchange interaction to see what happened to the system. Is there any instability of this trivial state, which we call a trivial quantum paramagnet? Instead of topological quantum paramagnet, it's a trivial quantum paramagnet. They all have the name TQP, right? So if you go from the trivial quantum paramagnet, increase the super exchange, and examine the instability of this trivial state, and what kind of state we can obtain by taking this kind of approach, right? So we can do that. We can do this mathematical mapping from spin variable to this U1 rotors. It's almost the exact mapping, and then you do coherent state path integrals and look at the instabilities. You look at when this bosonic rotor condense, and when the condense will induce the magnetism. So this bosonic rotor or this bosonic rotor that represents spin excitations within the trivial quantum paramagnet. It's originally fully gapped. The magnetic excitation in this trivial quantum paramagnet is fully gapped, but because it's a trivial state, all the excitation is gapped. As you approach as you increase the super exchange, the gap of this trivial excitation, the excitation of this trivial state becomes smaller and smaller. Eventually, when the gap of the magnetic excitation becomes 0, and these bosonic rotor or this magnetic excitation become condensed and induce magnetism. So this is how one can generate this phase diagram. So you start from this trivial state and study the excitation of this trivial state and trace the fate of this excitation of this trivial state and look at when this excitation becomes soft and condensed and induce the neighboring magnetic orders. So this is the idea behind. So this is the mathematics. I want to point out, although this state itself is rather trivial, we call it a trivial quantum paramagnet, but the excitation has some non-trivial features. So if you study the excitations, as you change inside this trivial quantum paramagnet, inside this quantum paramagnet, as you change the super exchange interaction, the ratio of J2 over J1, so the minima of this excitation, the magnetic excitation has the dispersion has some minima. If you trace this minima, and as you change this J2 over J1, so the minimum also evolves. Go from this discrete momentum minimum to a line, to a contour. Remember, this is a cut in this three-dimensional Brillouin zone. If you cut a two-dimensional plane and look at the energy kx, ky, and fix kz, right? So you go from here to here. So the band minima become from discrete point become a contour. So remember, this is just the one cut in the three-dimensional surface. If you construct the whole three-dimensional Brillouin zone, so this minimum will be a surface. Yeah. It's a gap. This is band minima. It's the minimum of a band. There is a gap below. There is a gap below it, right? So these minima actually they form a contour, form a surface in a three-dimensional Brillouin zone for different parameters. And this degenerate minima is actually the same as this degenerate spin spirals in the classical ground state manifold. It's a degenerate spin spiral. They form this surface in a three-dimensional Brillouin zone. And this is the quantum excitation. This is the quantum excitation of a trivial quantum paramagnet. The minimum of this excitation form a degenerate degenerate surface in a three-dimensional Brillouin zone. So as one approach, as one go inside these, so as one go inside these, approach this phase transition between this trivial paramagnet and ordered side, all these modes near this surface become more or less critical. They become critical almost at the same time and contributed to your thermodynamic property. So this is the boson. This is all the excitation near this surface are bosonic objects. They are not fermionic, but they become active or critical near the phase transition. So they contribute to your thermodynamics. So for example, they will lead to a linear T heating capacity. So we know to have linear T heating capacity, we must have constant density of state. This happens in Fermi liquid, in Fermi liquid metal, where all these modes on the Fermi surface become critical at the same time and contribute a linear T heating capacity. In this case, it's this bosonic degrees of freedom or bosonic excitations at this surface become critical and contribute to your thermodynamics. So this is an example of some interesting unconventional phase transitions out of trivial paramagnetic state. This state itself is trivial, but as you approach criticality, all these modes on this surface become critical at the same time. Yeah, it's a crossover regime. It's a if you go to very, very low energies, you will select the degeneracies. Some other perturbation will add on, right? But it's a regime that these modes become critical, right? Yeah. That's the topology of this minima. Yeah. It matters when it matters in some sense. So for instance, if you compare this one and this one, originally it wants to pick up a momentum along one direction. But if you go to this part, there's no moment, there's no intersection of this surface with one direction. In the end, you pick up a couple of momentums around this one direction. So this matters in that sense. When it gets into an ordered phase, it matters about the selection of order. But it doesn't really matter if you think about thermodynamics. All these, because as long as it's a surface, it will give you a linear T heating capacity near the criticality, right? So as you enter into this ordered side, then you need to worry about this, the system need to figure out the momentum to condense, need to figure out the wave vector to condense. What pick up this wave vector is through this quantum zero-point energy. They have different quantum zero-point energy for the momentum on this surface. They need to find a way to pick up. So the selection mechanism is through the quantum zero-point energy. This is called a quantum order by disorder effect. It's also been mentioned or introduced by SungBin yesterday. Yeah. Yeah. So this is just a simple-minded study on the competition between single ion anisotropy and super exchange interaction for spin 1. The frustrated spin 1 diamond antiferromagnet. So more recently, because of new experiments, we constructed this theory based on this much many abstract. Then we don't know the detailed information. Later on, there are detailed experimental information. So then we need to update the interpretation. So this is the magnetic entropy they published this year. So they carried out magnetic entropy measurement. What this plot can tell you is that so this nickel rhodium oxide, if one believes this data, so the entropy, the magnetic entropy is not R times log 3 for pure spin 1 moment. It's R times log 6. So that means in addition to a spin 1 local moment, there is actual twofold degrees of freedom being present in the system. So what is this actual twofold degrees of freedom? So this actual twofold degree is believed to be orbital degeneracy that can be present. So if you have nickel with 3d8 electron configuration in a tetrahedral environment, SungBin explained that in a tetrahedral environment, EG orbitals is lower than T2G, right? And further, because of tetragonal distortion, so the T2G is further split into this way. If it is split into this way, you put 8 electrons, and the lower EG is fully filled, and then you put the actual 4 electrons in the upper T2Gs. So there are two ways to put the actual 4 electrons in the T2Gs. So you can put it this way or this way. So it depends on where this actual spin is occupying XY, XZ or YZ orbitals. So there is the two-fold degeneracy. And this two-fold degeneracy or two-fold orbital degeneracy is responsible for this actual log2 entropy that is measured here. So this also actually speculated as a possibility in the end of the paper. So now because of this T2G is partially filled, and we know like spin orbital coupling has to be active at the linear order. This is also the physics responsible for various iridates and osmites. So then we need to theoretically consider effect of spin orbital coupling. So this is a partially filled T2G with fully filled EG. So you don't worry about EG. EG is quenched. You turn on the T2G spin orbital coupling. And this is the famous example. It's also been studied by Kalulin a couple of years ago, purely focused on D4 electron configuration in a T2G shells. This is the D8 configuration, but the EG is filled. So you don't worry about the EG. So this is equivalent to D4 electron configuration. So this spin orbital coupling tells you that so this effective spin is spin 1. This is spin 1. This is because Hans law tells you this is spin 1, s equal to 1. And if I don't worry about the splitting among the T2G first, and the effective orbital angular momentum is L equal to 1. So spin and orbital are entangled. They form J equal to 0 ground state. And the excited state would be J equal to 1 and J equal to 2. So this is the local physics. This is local spin orbit entangled physics, right? So that's the spin orbital coupling. And the strength of spin coupling is not that large. It's 10, 20 milli electron volts would be that kind of scale. It's comparable to super exchange interaction. So let me make a small digression. Because of this observation that for D8 electron configuration, because in a tetrahedral environment, EG is fully filled, so you don't worry about EGs. So that means D8 electron configuration is equivalent in a tetrahedral environment, crystal environment, will be equivalent to a D4 electron configuration in an octahedral environment. So then we have this correspondence between D8 and D4, with in an octahedral environment. Likewise, one can make this analog, make this correspondence for D9 electron configuration, which is copper. The copper 2+, copper-based spin nails, the copper aluminide, would be a perfect example. So copper will be equivalent to this one. This is iridium. So some physics of iridium, osmium, that can be possibly realized in this 3D transition metal oxides with copper or nickel. So this is the possible suggestion made in the paper. So now the minimal model become the competition between exchange interaction and the spin orbital coupling. So we still have J1, J2 exchange interaction for the local moments. Although it really should be a Kruger complex scale model, but that's the hard thing. If you really consider the spin orbital super exchange interaction, this is going to be very complicated. We don't know how to solve it in a nice fashion. So now we just assume the exchange part is a J1, J2 Heisenberg model, and in addition to this on-site spin orbital coupling, on-site spin orbital coupling, as I said, favors a spin orbital entangled singlet, which give you quench the local moment and a non-magnetic ground state. But if you turn on the exchange interaction would favor possibly some magnetism. So the competition between the spin orbital coupling, which favor spin-orbital entangled singlet, and the shift exchange, which favor various magnetism, lead to this this first diagram. So then is the first transition between spin-orbital singlet and the various magnetism. So we think maybe the system is inside the spin-orbital singlet. So imagine now, how do we test this claim that, like, if the system really inside this spin-orbital singlet, which is a trivial state? The spin and orbital is entangled, but the energy gap is renormalized by the shift exchange interaction. How do we test this claim? So then one idea is to use external magnetic field. So this is the plot of the response of the system on the external magnetic field. So you add a field into the system. What the field do is as follows. So this plot is not very easy to understand. So the simple picture is as follows. So this is the local energy levels. So now you add the field. The field will split the J equal to 1 triplet and J equal to 2 these 5-fold degenerate states. So this become split into JZ equal to 1, JZ equal to 0, JZ equal to -1. And as you increase the field strength, so these triplons will be dragged down. And eventually when the field is large enough, there will be a level crossing. So this triplon will touch 0 energy and will condense. So this is the example of field-driven, field-induced triplon condensation. But there are two triplon, two kinds of, this is an example of triplon the field-induced triplon boson-Einstein condensation. But in addition to the dragging down of this J equal to 1 triplets, the J equal to 2 state can also be further dragged down by magnetic field. So if you further increase the strength of magnetic field, so you will get another phase transition by dragging down this object. So that means in this plot, if you start from a spin-orbital singlet, imagine you are here with larger spin-orbital coupling, spin-orbital singlet. Now you increase magnetic field this way, increase magnetic field. First, you drag down this J equal to 1 states, you get a magnetic order. You get a so-called triplon boson-Einstein condensation. You get a phase transition. But then if you continue to increase the field, you get back to the spin-orbital singlet. But then you further increase the field, so the J equal to 2 state will be dragging it down. So you get another phase transition. And when field is large enough, you get fully polarized. Every spin parallel to each other. That's the end. So this is the plot of for different strengths of this spin-orbital coupling. For this largest spin-orbital coupling, which is this plot, you can see this blue curve is in-plane magnetization. There are two bumps. With two bumps that corresponding to these two re-entrant transition in this green part. Yeah. So this is different. One can make a comparison to these. One can make some interesting comparison with other related systems. For instance, one can make comparison with this thing is probably called a ham purple, which is a famous southern Shastree lattice with dimerized spin singlets. So in this material, the copper from this southern Shastree lattice and the interaction on the black link is very large, much larger than the exchange interaction on the dashed link. So the ground state will be a simple spin singlets formed on these links. So now imagine you apply magnetic field to the system. So originally for each link, for each this black, the border color link, the ground state is a spin singlet, and the excited state will be a spin triplet. And applied field will split the triplet into this. And when the field is large enough, this triplet is dragged down. So you get level crossing. You get a phase transition. So this is the in-plane magnetization. You get a bump in the in-plane magnetization. So you get a triplet BEC by applying magnetic field. Because locally on each dimer there is only one triplet, or one S equal to one state. So there is only one transition. In contrast, in this D8 diamond antiferromagnets, they are, in addition to J equal to 1, they are J equal to 2. So each time you drag one down, there is a first transition. So here you drag you put this, you drive this down, you get another transition. So there are two transitions. So this is much similar to the spin 1 dimer, where there are, in addition to spin total S equal to 1, and then total S equal to 2. So there will be two transitions. So that will be a very interesting model system to understand the triplet condensation by applying magnetic fields. So yeah. So in the paper, it's a very interesting paper by Kalilin, which they studied this D8, D4 motor insert upon doping. So as I said, there is a correspondence between D8 electron configuration on the tetrahedral environment and the D4 electron configuration on the octahedral environment. So in this beautiful paper, so they suggest that if you dope electron-hole dope this D4 electron configuration, with spin-orbital coupling, so you may obtain ferromagnetism and possibly triplet, topological symmetry activity out of this doping of spin-orbit entangled D4 electron states. So without much creativity, one can make this simple correspondence. If one dope this system, you can obtain topological symmetry activity. If one dope this D8 system, one may also obtain topological symmetry activity by this electron hole doping. So this is just a simple suggestion. Yeah. So this is the this is summary plot for the field of strongly spin-orbital coupled correlated materials. So when you have spin-orbital coupling and strong correlations, you can stabilize various phases. And people, including me, we suggested that maybe it is more reasonable to think about this kind of physics in the context of heavy ions, such as iridium, osmium, or even these 4F rare earth atoms, where spin-orbital coupling is very strong. At the same time, correlation effects is strong. Now, through this work, through this correspondence, we can now think, even in this 3D transition metal oxides, where the spin-orbital coupling is not often that strong, but such physics of strong spin-orbital coupling may even emerge when there is orbital degeneracy. So when we should carefully think about the effect of spin-orbital coupling in the orbitally degenerate 3D transition metal oxides, such as this nickel or copper-based spin nano compounds. Finally, let me summarize. So we'll point out this guy is probably not a topological quantum paramagnet, maybe something else. There's some interesting competition between either on-site spin-orbital coupling or single anisotropy with the super exchange interaction. And this competition led to a very interesting, emergent quantum criticality and some interesting, low energy modes out of it. And yeah, thank you very much. Yeah.
Some questions during the talk, but there is time for more. So questions.
So here, yeah. So you have made a remark that the log2 difference in a specific heat is due to this orbital degeneracy. And when you cool the system sufficiently down to low temperature, do you expect some kind of structural, nematic order, so that the structural symmetry is further lowered from tetragonal to orthorhombic?
No, there's no such indication. So the log2, if it is cubic symmetry, you would have actual log3, because there's a threefold degeneracy of the T2Gs. Mm-hmm. But because around the 400 Kelvin, there is a cubic to tetragonal phase transition. So So the orbital degeneracy is the perfect threefold degeneracy is being broken. So, but it still have twofold degeneracy, and this twofold degeneracy is responsible for this actual entropy below this 300 Kelvin.
That's right. So I was mainly referring to the iron-based superconductors, where there is also a twofold degeneracy concerning the orbital degree of freedom.
Yeah.
Where then they can have a nematic phase or orthorhombic phase, but it doesn't happen here.
It's not obvious it's happening.
Okay.
No, it's not obvious. Yeah.
Okay. Thank you.
So maybe two parts. So I was just a little confused with the link. So the earlier part, you spoke about on-site anisotropy, which would give you a trivial paramagnet. And then there's the spin-orbit coupled possibility, which is also a trivial paramagnet. So is there a way to distinguish both between the two of them?
Yeah, so,
and perhaps one more related question is, experimentally, is there a way to distinguish between a topological paramagnet and a trivial paramagnet?
Yeah, let me first answer the first question. So experimentally, it seems to suggest the latter, the spin-orbit coupling is important, which is not considered in the first part. In the first part, because of the time reason, the data hasn't existed around that time, right? So now we have this entropy measurement, which seems to indicate the importance of orbitals. Yeah, so that suggests that maybe this spin-orbit coupling or spin-orbit entangled singlet may be more relevant, maybe possibly more relevant than the trivial quantum paramagnet from the single anisotropy. Yeah. So for the second question, how to distinguish between a trivial topological from a topological paramagnet and a trivial quantum paramagnet, I don't know. So it's associated with this unclear understanding about the surface states of a 3D topological paramagnet. Many things can happen. For the surface of a 3D, for the correlated 3D topological paramagnet, the surface can be, for instance, can be an intrinsic topological order, with the fractionalization going on. It's rather exotic. The other possibility is that the surface has a symmetry breaking. The bulk preserved all the symmetries without any magnetism, but the surface can break the symmetry and induce some ordering. That can also happen. It can also the third possibility is maybe there are some gapless edge states, gapless surface states on the surface. So it's not very clear, but the way to distinguish between a topological paramagnet and a trivial paramagnet must be through the surface or through some defects in the bulk. Yeah, but the precise property we don't know. Yeah.
If not, let's thank Gang once more. And
Thanks.